In this lesson, we're going to cover section 4.4, which is dealing with pH, which you've probably heard about, and pOH. We've got three goals for this section. The first one is to describe what the pH scale is and why it's used. We're going to calculate the pH and pOH of solutions if we're given the concentration of hydronium or hydroxide. And then finally, we're going to do the flip side of this. We're going to calculate concentrations of hydronium or hydroxide given the pH or pOH. So next, why the pH scale? Why do we care about it? The pH scale is an incredibly important parameter. It plays a role in a lot of different things, mainly with water quality applications as well. So you can see with pH scale, we sometimes use it to measure a water quality, and depending on what the pH is, will depend on how the water tastes. If it's something that's acidic, it'll taste slightly fresh, kind of lemony. If it's neutral, it'll be a very bland kind of taste. And if it's alkaline, it will be something you don't want to drink at all. It's quite inedible. With food preservation, pH scale is used. A lot of foods are preserved with citric acid or with vinegar, two acids used for food preservation. Pollution as well. You can see that the picture on this page is of acid mining, and the mining tailings are running out and is polluting the lake or the river. And then lastly, wastewater treatment as well. A lot of permits with wastewater treatment are pH dependent as well. So there's lots of applications in this unit. So the first thing that I thought we'd do is a little warm up. So this is using some of our information from previous lessons. We're going to first find the concentration of hydronium in a 1 molar solution of hydrochloric acid at 25 degrees Celsius. And then we're going to do the same thing for a 1 molar solution of sodium hydroxide at 25 degrees Celsius. Now, as you might remember, hydrochloric acid is a strong acid. And because it's a strong acid, it behaves differently than, say, a weak acid. Strong acids dissociate 100% in water. So they actually have a hydrogen that splits off. That hydrogen ion will form hydronium with water, but we get 100% ionization. So the way we can say is if we're finding the concentration of hydronium in a 1 molar solution of hydrochloric acid, because this is a strong acid, we can show that HCl plus water, one-way arrow, it's going to form a hydronium plus a chlorine ion. With this, that means that the concentration of hydronium is in a 1-to-1 ratio with the hydrochloric acid, so it's 1.0 moles per liter. Okay. Now the next one is find the concentration of hydronium again in a 1 molar solution of sodium hydroxide. Now the sodium hydroxide is also a strong base, so it's going to ionize 100% as well. When we take that sodium hydroxide, it's going to dissociate completely, and we're going to get a sodium ion and a hydroxide ion. 1-to-1 ratio, that means that the concentration of hydroxide is 1.0 moles per liter. However, that's not what the question's asking. We're going to have to go back to the last lesson where we were looking at the ionization constant of water. And we've got this ratio. We know that Kw is equal to the concentration of hydronium multiplied by the concentration of hydroxide. And at 25 degrees Celsius, that Kw is a constant, 1.0 times 10 to the negative 14. So when we substitute in the 1.0 moles per liter of hydroxide here, we can see that the concentration of hydronium is 1.0 times 10 to the negative 14 moles per liter. And if you take a look at these powers here, I've told you to remember these powers. This is 1.0 times 10 to the 0. If we look at 0 and 14, if you know anything about the pH scale going from 0 to 14, you might now start to put together the pieces of why that pH scale goes from 0 to 14. What we're looking at is relating it to concentration of hydronium. So that's where we're going with these things. So throughout this whole lesson, I'm going to be talking about acid land and base land. I know it's kind of crude. Acid land, we're talking about things that are dealing with hydronium or hydrogen ions. So anytime we're talking about H3O plus or hydrogen ions or things like pH, I'm talking about things in acid land. And anytime I'm talking about hydroxide or pOH, I'm talking about base land. So we're going to be talking about these two different things, and we're going to be looking at ways of crossing from acid land to base land. In the previous question, all of our answers had to be in acid land. We were dealing with hydronium. To get from that base to the acid, we had to do a conversion. And so this is the one set of conversions that we learned the other day. We looked at how to figure out hydronium from a hydroxide or hydroxide from a hydronium to kind of cross that bridge, go back and forth. What we're going to be looking at today is all of these different ones that you can kind of see kind of whited out below, looking at how we get from an acid to a pH, and from pH we're going to relate that to pOH and kind of go back and forth. This table you'll find in the summary page if you've printed off the notes, and I'm going to kind of refer to it as we go through the lesson. Okay, first, the pH scale though. Why do we use a pH scale? It's been around and we've been using it for the past 110 years. It was kind of invented by Sorensen, and Sorensen actually should have a little cross over the O, it's a little accent. Okay, he was a Danish chemist. And it's a way to specify the concentration of hydronium in a solution. pH stands for the potency or the power of hydrogen. And as a scale, it's a really practical scale. If you were to say to, just a normal person who hasn't taken a chemistry class that I've got 1.47 times 10 to the negative 6 moles per liter of something, it's a little awkward. People don't usually speak with scientific notation in mind. Whereas if you tell them it's a pH of 5.8, it makes that number way more accessible and acceptable in any kind of non-sciencey publication. When we have very acidic solutions where pH is around 0 or less, yes, pH actually can be negative. The scale is not confined from 0 to 14, just kind of conventionally used from there. We usually use the concentration of hydrogen because it conveys a better sense of the concentration than pH, but there's no true upper and lower limit to this scale. Now, the pH scale works as a logarithmic scale. It's a logarithmic scale. So kind of if we go from a pH of 1 to a pH of 2, a pH of 1 is actually 10 times more acidic than a pH of 2. And pH of 3 is 10 times less acidic than 2. So it works on a base 10 scale. So it's kind of a practical scale. Other applications of this are the Richter scale. So if we look at an earthquake, if you have an earthquake that is 5 on the Richter scale, and then another earthquake is 6 on the Richter scale, that earthquake that was a 6 is 10 times as damaging as the one with 5. So that's what a logarithmic scale is. You can see the two graphs here showing what the difference between that linear scale is and a logarithmic scale. One thing that you want to check out here is the numbers. And even cases of COVID-19 have been more regularly looked at with a logarithmic scale in recent, particularly when you're comparing countries and things. Because you have lots of countries that have numbers kind of in the 1 to 1,000 range. Not that many countries with this range of 10,000 and more. And so if we want to compare them, a logarithmic scale makes it so that you can see them far more easily. So how do we calculate pH and pOH using this logarithmic scale? Well, this is when your grade 12 math really comes into play, because when we're calculating pH is equal to negative log the concentration of hydronium. There is our calculation for pH. And you will notice that the pH has no units. Now, what does this look like? Well, we said earlier that if we had a concentration of hydronium equal to 1.0 moles per liter. The pH for this is actually 0. And the way we get that pH is we did the negative log of 1.0. If you plug that into a calculator, negative log 1.0, you'll get 0. And the way to kind of look at this is another way of writing 1.0 moles per liter is 1.0 times 10 to the 0 power. That's where we get that pH of 0 from. It's really referring to that exponent there. If we had a concentration of hydronium equal to 1.0 times 10 to the negative 14, like we did in that 1 molar sodium hydroxide solution, well, when we type that into our calculator, negative log of 1.0 times 10 to the negative 14, we end up with a pH of 14. So again, we're taking that, and you'll notice that we've gotten rid of the negative sign. That's where that negative log comes from. One special note about sig figs is that in pH, we actually start counting sig figs after the decimal point. And the reason for this is because we're kind of looking at this with the negative 14 here. So we kind of look at it after that decimal point because the 14 with that pH is just implying how big that power is. It's not actually telling us how precise it is. So we actually look at that after the decimal point for how many sig figs we're looking at, how precise that measurement is. So the example question here says, find the pH of a solution where the concentration of hydronium is 3.5 times 10 to the negative 3. We're going to take negative log 3.5 times 10 to the negative 3. Totally urge you to pause this video, get out your calculator right now, actually take the time to get this out and try it. What we'll find is the pH is 2.46. So you'll notice I had 2 sig figs in the question here. I'm leaving 2 sig figs after that decimal point there. So there's my final answer, no units. Now pOH is not as commonly used, but it can be calculated as well. Same kind of calculation. We take pOH equals negative log, and this time we're in a baseland calculation. So we're looking at the hydroxide situation here. So if we're going to find the pOH of a solution where the concentration of hydroxide is 2.86 times 10 to the negative 12, again, we're just going to go pOH equals negative log of 2.86 times 10 to the negative 12. And this time I get 11.544. We're looking 3 decimal places for 3 sig figs. Now we're going back to acid land and base land for just a second. So what you can see here is that we had Kw values that helped us get between hydroxide and hydronium on this side. What we just did was we figured out paths between the hydronium calculation, or H plus, this or H3O plus, and pH. So that was that calculation that we just did there, and pOH. So we're kind of looking at 2 ways to getting into a more readable scale. What we're going to do next is relate them to one another. How are pH and pOH related? Well, at 25 degrees Celsius, what you'll have noticed is that pH plus pOH is equal to 14. So that's where we talk about that 14 scale. And the reason for that is the Kw. Kw, which related our acids and bases, our hydronium and hydroxide, at 25 degrees Celsius, Kw is 1.0 times 10 to the negative 14. That means that my pKw, if I took the negative log of that number, is 14. That's where that number comes from. So if a temperature in one of your problems is not at 25 degrees Celsius, then pH plus pOH will be equal to whatever pKw was. So you can take the negative log of Kw to find out what that number is. Okay, for our next kind of example question, it says, what is the pH of a solution where pOH is 9.83? Well, my pH is going to equal 14 minus 9.83. So pH is equal to 4.17. Again, no units, keep the same number of sig figs. Okay, so that relates those two things together, how we switch between pH and pOH. So it's, if we're dividing our chart into acid land and base land, this is like a second bridge between the two areas of the land. Go back to this one, hopefully it won't erase all my data. Okay, a 100 milliliter sample of aqueous solution labeled 0.1 molar hydronium is diluted to 1 liter. Has the pH of the solution increased or decreased, and by how much? Now, if we're diluting to 1 liter, if we use our C1V1 equals C2V2 calculation, we can actually calculate exactly how much, what the molarity of this new solution is going to be. We could also do it just using logic as well. So we start with 100 milliliters. We're finishing with 1,000 milliliters. And so our new concentration is going to be 0.010 moles per liter. So what the pH is doing, pH is going to be increased because we're not as acidic, and it's going to increase by 1. Okay, we're 10 times more dilute, so we're actually increasing our pH by 1. Okay, next is kind of working backwards, where we want to find the concentration of hydronium from a pH or the concentration of hydroxide from a pOH. So this is kind of doing an inverse log or an anti-log, trying to do the opposite. If we want to find a concentration of hydronium, what we're going to do to go backwards, now we remember that our log had a base of 10, so what we're going to do is we're going to take that base of 10 and we're going to raise it to the negative pH power. Same thing if we want to do this with hydroxide, we're going to take that base 10 to the negative pOH. Okay, so sometimes I'll refer to this as an anti-log, okay, or an exponential function. Going backwards from pH to hydronium, you can see that I count the sig figs after the decimal place, so I have 2 sig figs here. And to get my hydronium, I'm going to take 10 to the negative 3.34, giving me a concentration of 4.6 times 10 to the negative 4 moles per liter. So I'm going to finish these up. Again, please try them and make sure that you understand how to go from one to the other. And this one I'm looking at 3 sig figs, 2.462. Okay, for question 2, it says, during a titration, the pH at the equivalence point changed quickly from 4.35 to 9.65. Calculate the concentration of hydronium just before and just after the equivalence point was reached. So just before, we're looking at a pH of 4.35. If I want to figure out what the concentration here is, the concentration of hydronium is going to be equal to 10 raised to the negative 4.35. So beforehand, my concentration of hydronium is 4.5 times 10 to the negative 5 moles per liter. After, the pH is 9.65. So my concentration of hydronium is equal to 10 to the negative 9.65, or 2.2 times 10 to the negative 10. Next question, it says, a student calculates the pH of a sample of concentrated nitric acid to be negative 1.2. She thinks she's made a mistake because the value is negative. And that would be an easy mistake to think you've made because mostly we talk about pHs between 0 and 14. Calculate the hydronium concentration in this acid solution and decide if an error was actually made. So we're going from a pH to a a concentration. So again, we're going to use the anti-log 10 to the negative 1.20. And I get a concentration of 16 moles per liter. Now, if I'm thinking to myself, is that possible? Yes, it is possible. So it is possible to get a negative pH. Doesn't happen all that frequently, but with a strong acid, it definitely can happen. So I can conclude that the concentration of that nitric acid is something that I'd probably find in a chemical storeroom, 16 molar solution, and yes, that is possible. Now, why do you think expressing pH values for concentrated strong acid solutions not really necessary? With this one, expressing it as negative 1.2, it's probably just easier expressing it as a 16 molar solution. We're not using scientific notation here. There's no point in using scientific notation, no point in using negative values either. Okay, last topic that we're going to look at today is working backwards. No, wait, we've done this already. So forget it. Okay, last thing we're going to do here today is kind of take a look at this summary and do some sample problems that include everything. So with this summary, you can see now that we've actually covered everything on this chart. This part right here was all looking at kW. So we had that 1.0 times 10 to the negative 14 is that value that connected the concentration of hydronium and hydroxide. These ones going down the sides are when we were looking at logs and anti-logs. Okay, and we did that for both pH and pOH. And then finally, this last one connecting pH and pOH, our second trip over the acid land, base land bridge, is relating pH and pOH to that 14 on the scale. With this whole chart, we are assuming 25 degrees Celsius for everything here. And that 1.0 times 10 to the negative 14 would change if we don't have 25 degrees Celsius. Same with that 14 over the other bridge. So it's all very temperature dependent. Okay, a couple of last sample problems before we finish off today. So we've got a 0.1 molar aqueous solution of aspirin. So this is acetylsalicylic acid. At 25 degrees Celsius is found to have a pH of 2.27. So looking first at this 25 degrees Celsius, we're not going to use that in our calculations, but what that 25 degrees Celsius tells us is that kW is equal to 1.0 times 10 to the negative 14, and it also tells us that pH plus pOH is equal to 14. So it gives us two pieces of the puzzle that we can kind of use to connect this. So it says calculate the concentration of hydronium, concentration of hydroxide, and the pOH for this solution. And there's a number of different ways of solving for this. First one that I'm going to go for is the concentration of hydronium. So I know that the concentration of hydronium is equal to 10 raised to the negative pH. So there's the first one that I'm going to do, and I get 5.4 times 10 to the negative 3 moles per liter. Second one that I'm going to do, and I could get this from a different value as well if I want to. My concentration of hydroxide, though, is I'm going to take the kW 1.0 times 10 to the negative 14, and I'm going to divide that by my concentration of hydronium, 5.4 times 10 to the negative 3. When I do that, I get 1.9 times 10 to the negative 12. Lastly, when I want to look at pOH, I'm going to take 14 minus 2.27, and I get 11.73. Now, for some of you, if you were looking at this, maybe this is not the calculation that you would have done, because there's another way of getting this as well. If instead I take that pOH, I can calculate the concentration of hydroxide by taking 10 to the negative 11.73. And if you do that in your calculator, you'll also get 1.9 times 10 to the negative 12. So Same answer, completely same answer, different way of getting it, and you can do it either way.